Measures of central tendency. When we have a large data set, such as the historical returns on stocks, we need measures to indicate how the data is centered. So imagine we're looking back at 100 years worth of stock index returns. Now that would be a lot of observations. So what we want to do is we want to see if there's a value towards which most of these observations are centered around. So that center value will give us a good idea with respect to the entire data set. So now we're going to look at these various central tendency measures. Now the most often used is arithmetic average, also referred to as mean. And this is the most basic average calculation. We simply add up the values for all the observations, and then we divide it by the total number of observations. Geometric average, or geometric mean, on the other hand, incorporates the effects of compounding. In other words, it takes into account interest or return earned on previous income that has been earned. And let's demonstrate that with an example. Suppose that over the last 4 years, a portfolio exhibited the following returns: 5, 8, 13, and -1. And again, we want a central tendency value, or that value towards which most of the data is centered around. So the first thing we could do is we can calculate annual arithmetic average. And as we've seen before, we just add up the values for all the observations, and we divide it by the total number of observations, which is 4, and that gives us 6.25. However, by simply adding up these returns together, what we're doing is we're assuming that no compounding is taking place. In other words, we're assuming that the returns are not being reinvested. For example, if we start with $100, so if we start with $100 at the beginning, in year 1, we would simply earn 5% of that 100. So there it is. So start with $100. If you're going to earn 5% in year 1, for the year, you would have made $5. However, in year 2, because we're just looking at 8% here, we're assuming that we're going to earn 8% of 100, or $8. So see, by simply adding up the returns for each year, you're not taking into account the compounding effect. So you're not assuming that the 8% in year 2 is being earned on the 5% that was earned on year 1 as well. So that's why when we're computing arithmetic average, you have to be mindful of these limitations. In other words, with arithmetic average, we're assuming no compounding, and therefore the returns are not being reinvested. So therefore, arithmetic average would be ideal in this kind of scenario where the investor says, I just want to take my profits out so that in year 2, when you do earn 8%, you're still earning it on the original capital because you withdrew whatever returns you had made in year 1. Now with the geometric average, we do take compounding into account. In other words, we do assume that there's reinvestment. And here's the way it would unfold if we were calculating geometric average. So again, we assume that we're starting with $100. And the first part of the calculation over here says, okay, bring forward your $100 and we're going to earn 5%. So at the end of the year, you would have $105. But look what happens in the second year. So again, you get 1 plus, but the 1 now applies to the 105. So do you see how you're reinvesting the $5 you earned in year 1? So now in year 2, when you earn 8%, the 8% is being earned on 105. And that, ladies and gentlemen, is compounding, i.e. in year 2, we're earning the return, not just on our original principal, but we're also earning return on whatever earnings we accumulated in the previous period. And you can see why compounding is associated with reinvesting, because the only way you could earn 8% on the 105 in year 2 is if you reinvest that 5% you earned in year 1. And of course, this process keeps repeating until you reach the end of the 4th year. But the thing with central tendency is I want one value. I just want one value that represents the data over the last 4 years. So here's the way we set it up. So $100 growing at these individual rates of return should have the same ending value as the $100 growing at the annual geometric average return, but compounded 4 times. Why compounded 4 times? Because the G here is annual. So if you want both sides to equal, both sides would have to cover 4 years. So once you get it down to this stage over here, it just becomes linear algebra, meaning that you got one equation and one variable, so we can solve for G. So therefore G, so if you solve all these numbers and then solve for G, you get 6.128% for the geometric average return. And as I said before, this geometric average includes compounding effect. In other words, we assume that the returns are being reinvested each year, and we demonstrated that as well. So just very quickly, same illustration, $100 in year 1, we would earn $5, but then in year 2, under geometric average, you could see that we're earning the 8% on the 105, and I showed that as well. So you could see that algebraically. So when we have this term here, you're making 8% on the 105 from the first year. So in effect, you're getting 8%, not just on the original principal, but whatever returns you earned in year 1. Therefore, for the same data set, because it was the same data set, we looked at the same 4 annual returns. You could see that the geometric rate or geometric average of 6.128 is less than the arithmetic, which is 6.25. Now, why is that? Here's the logic. Since the geometric average compounds, in other words, it does more work, you need less of it to explain the same return series. And here's what I mean by geometric doing more work. So you're earning interest on interest, and that's what I mean by it's doing more work. And I have an analogy that I'll share with you, and hopefully that'll ingrain your knowledge of this relationship. Suppose that the doctor prescribes a more potent medicine. So if the medicine is more potent, how would the dosage be affected? So the more potent the medicine, the lower the dosage. So you need less of those pills in order to cure the ailment. It's the same thing here. Geometric does more, so it's more potent. So you need less of it to explain the same return series. Now the next measure of central tendency is weighted average. And let's have a look at an example to see how weighted average works. Suppose we're looking at a portfolio, and this portfolio has 3 stocks, A, B, C. And what we need to know about a portfolio are 2 main things. First of all, how exposed is the portfolio to each stock? So what's the weight? So we got 20% in A, 50% of the portfolio in B, and 30% of the portfolio in stock C. And then we just need to know how each stock performs, so 12, 8, and 23. Okay, so how did your portfolio do? Well, portfolio return would simply be the weighted average of the returns of its individual components. So ladies and gentlemen, a portfolio by itself is just a basket. It's not an independent variable. So how the portfolio does is really a function of how the underlying stocks did and how exposed the portfolio was to each stock. So here's the mathematics. So portfolio return is equal to, so look at the way I laid it out. So first let's look at our 3 stocks, and what do you need to know about each stock? What was the exposure of the portfolio to that stock, and how did that stock do? And we do that for all 3 stocks, and then when you do the math, you get a weighted average return of 13.3. So quantitatively speaking, this 13.3 is weighted average. But for all intents and purposes, this is really our portfolio return. So portfolio return is basically weighted average return of its individual components. Now the other measure of central tendency is called harmonic mean. So first I'm going to show you the framework. So there it is. But I don't like memorizing formulas. So now I'm going to show you a ground up approach in order to get the same answer as if you had used that formula. Now here's the trick. Harmonic mean is a special case of weighted average. So here's our example. Suppose that you invest $500 per month for 2 months, and the $500 goes into buying stocks. And this is very common. So a lot of people have this monthly plan for investing. They'll just say, I'm just going to put in $500 per month, and I'll just buy as many shares as I can with the $500. Now, of course, the stock price will change. So in the first month, there's your $500, but the stock price is $5. So you're able to buy 100 shares. Great. Month 2, again, you invest $500, but by then the stock price is $6. So the $500 only gets you 83 shares. So now let's total everything over the 2 months. You invested a total of 1,000, and you were able to buy 183 shares. So now look at I'm going to compare 2 measures. I'm going to look at the generic weighted average, and I'm going to look at harmonic mean, which I refer to as special case of weighted average. Now here's why the two are related. Because they both use weights. So we have 2 stock prices. We like to know what the central value is for the stock price, if you will. Now, if you're using weighted average, the weights would be related to how much you invested each month. So here's month 1, here's month 2, and look at it. You invested a total of 1,000, so 500 each month. So each month gets 50% right there. So therefore, the month 1 stock price was $5. That gets a 50% weight. Month 2 is $6. That gets a 50% weight. So your weighted average would be $5.50. That's straightforward enough. But look at harmonic mean. With harmonic mean, the weights are based on how many shares you purchased each month. So it's right here. So with weighted average, you're looking at this. With harmonic mean, you're looking at this. And that's the difference. But they're both weighted average. It's just a question of what variable do you use to construct your weights. So, if that's the case, in month 1, how many of the 183 shares were purchased in month 1? So 100. So what was the price in month 1? $5. Okay, so there it is. Done. And month 2, what happened in month 2? So first let's determine the weight. Well, out of the 183 shares that we bought, 83 came from month 2. Okay, so there's month 2. That's the weight assigned to month 2. And then what was the stock price in month 2? It was $6. So there you have it. And then that's it. That's it. And then if you're calculating harmonic mean, your answer would be 545. But now I'm going to show you how you would have got the same answer using that formula. Right? So you see how we got the answer first using a ground up approach? And then I'm going to show you how the formula would get you the same thing, except this requires memorization. However, the ground up approach forces you to understand what really is going on. But nevertheless, you'll get the same answer. So we had 2 months and 1 over xi. So xi is the variable you're trying to find the average for. In this case, it's stock price. So there's your month 1 stock price, month 2 stock price, and you get 545. Now, tip. Harmonic mean is lower versus arithmetic mean and weighted average. So you can see that right here, right? So here's the harmonic, it's 545, whereas weighted average, it's 550. Now, why is that? Why is harmonic mean lower relative to arithmetic and weighted average? Because when the stock price was lower, we were able to buy more shares, so put the two together. So therefore, more shares means more weight when the stock price was lower. So of course that's what's going to happen, right? When you're assigning more weight to the lower stock price, harmonic mean will be lower, of course. Now let's look at median. Median gives us the value of the middle observation in an arrayed data set. So let's have a look at an example. Suppose we're looking at a return series. So here's the raw data, right? So the first thing you got to do, and remember this on the exam, ladies and gentlemen, first thing you got to do is you got to rearrange the data. So from lowest to highest. So here we go, 2, 5, 7, 9, 15. All right. And step 2, median is just the middle value. So, you know, start from the outside, work your way in, and this is the middle. So the median is actually 7. Now, of course, real life is not that simple where you're only given 5 observations. You will be given large data sets. So we need a framework to identify the median value. So with 5 observations, which is an odd number, the median was the 3rd observation. Now, how did we get 3? So from 5 observations, so this is how I'm going to build up the framework. From 5 observations, how did we identify the 3rd one as the median? So I just need a framework that takes me from 5 to 3, and here it is. So 5 plus 1 is 6, divided by 2 gives me 3. So now I just got to plug in the variables. So the 5 was really n, which was the number of observations. So there it is, ladies and gentlemen. Once again, using ground-up approach to get whatever framework we need. Now suppose we add another observation so that we have 6 observations. In other words, even number. So now the return series, here it is. It's the same. So you have the same original 5 observations, but now I'm going to add a 6th one. So now we have a total of 6 observations. So again, you know, let's have some fun. Let's do this manually. Start from the outer ends and work your way in. And you can see that we have 2 values in the middle. So what we got to do is we got to find the average of those 2. That'll be our median. Of course, the average between 7 and 9 would be 8. So now I need your help to construct a framework. From 6 observations, how did we identify the 3rd and the 4th observation? So there it is. From 6 observations, how do we get the 3rd one? Well, how do you go from 6 to 3? 6 divided by 2. And there it is. So 6 is the n. And how did you get the 4th one? So how do you go from 6 to 4? 6 plus 2 is 8, divided by 2 is 4. So it would be n plus 2 divided by 2. So when you have an even number of observations, the median is the average of the 3rd observation found that way and the 4th observation found that way. Now note, median only looks at the value of the middle observation, whereas arithmetic average looks at the value of all observations. So therefore, the arithmetic average, because it is looking at all observations, including outlier or extreme values, the arithmetic mean will be affected by these extreme values. To demonstrate, let's have a look at this first data set, right? 2, 5, 7, 9, 15. As we saw before, so this is information that data that we did illustrations for before. The median was 7. And if you find the arithmetic average, so if you just add all these up and divide it by, you know, what is that, 5, you would get 7.6. But now watch what happens when I add an outlier. And that, ladies and gentlemen, that's what an outlier is. Look at this. You got these small numbers, and then boom, all of a sudden you get 370 right there. So clearly that's an outlier, an extreme value. But look at the median. Median says I only care about the middle value. So you can add, this could have been 370 billion for all we know. It would not have affected median because the median just focuses on this. And as we saw before, the median would be 8, the average of these 2. However, arithmetic, actually it would add up all these numbers and then divide it by 6, and then you get 68. So what this demonstrates is that, yes, the arithmetic is very much affected by the outlier values. Now let's look at mode, which is our final measure of central tendency. Mode is the value or the values that are observed the most number of times. So for example, suppose that we're looking at the following data set, and which numbers occur the most number of times? I got 3 and 6. They occur the most number of times. So there it is. The mode is 3 and 6. So this would be called a bimodal distribution because you got 2 modes in this distribution. So this is called the distribution right there. And so therefore note, for a given data set, you can only have one average. One average. So suppose you're looking at a classroom. So that's what the data set is. Let's pretend it's a classroom that's got 100 students. How many class averages can you get? Just one. One class, one average. How many medians can we get? Just one. In other words, what's the middle value grade among all the students? There could be one middle value. However, it is strongly possible that few students will get the same grade. Right? So you can have, let's just say, a cluster of students that got 75 and another cluster of students that got 85. So you could have more than one mode in a distribution. And the second note, the same framework for central tendency applies to both population, which includes all observations, and a sample, which is only a subset of the population. So here's the distinction between the two. So this here, the entire pie, would be the population, whereas this would be the sample. And what this last note is saying is all these measures of central tendency that we calculated, we could have used it for either the population as a whole or just the sample. The mathematics would be the exact same.